All right. Hello, everyone. So today we're going to continue on with learning about linear regressions. In class this week, we will have covered hypothesis testing for linear regressions. So we'll do a little bit of review on running the linear regression, but then also interpreting the coefficients, standard errors. And then we also are going to discuss how we do hypothesis testing with kind of robust assumptions on the unknown part of the linear regression, that bit u. Remember, we have y equals beta 0 plus beta 1x plus u, u being kind of the residual term, the error. So we don't know much about it, but in class this week, we'll have learned that there's various assumptions we can make about it. And we want to make as few assumptions about it as possible. So let me stop talking and kind of get into the coding. So we're going to use a data set on TV show ratings this week. So let's create a new script. All right, let's make sure that so this is lecture 4 demo. Let's make sure that we attach tidyverse and ggplot. There's two new packages that we need this week. So the packages are lm test and sandwich. Okay. These packages we'll need for when we do testing of hypotheses with kind of these robust errors in our linear regression. Okay. So you should be able to run these two just fine. But if you haven't installed lm test or sandwich yet, remember you'll need to do that. So you'll need to go to packages, install, and then search for lm test. So you'd click that and then you'd click install. Once you've installed it, then you can run this library command, which will attach it, right? It'll check mark the package in our list of packages. You need to install it first. Now, you don't need to install a package every time. You need to install it just once. But every time you reopen R, you need to reattach the packages that you want to use. Okay. So install from here, install only once, run the attachment code every time you want to use that package. Okay. The next thing we do is, of course, we find wherever we stored our data. So for me, data is here. So let me read it in. I think this is called Star Trek TNG ratings. And we will read CSV like usual. Oh yeah, and usually we have, yes. So I'm doing it a little differently today. Usually I would go file, import data, and then I would take the little snippet of code once I found the data. And that's fine. You can kind of still do that. Here, I'm just kind of like writing it out by hand without kind of going through that process. Okay. So we're going to read this file. And of course, we'll attach these other two packages, lm test and sandwich. Okay. And then we'll read this file. All right, let's take a look. We have 176 observations of 6 variables. So this is a file which provides ratings, so user supplied ratings for a TV show. Okay, so we can see the variable names are fairly informative. We have season, we have episode, and then we have the name of the episode. We have what year did that episode air, how many people voted on kind of the rating, supplying ratings, and then we have the rating number itself. Okay. So good. So this all looks like it makes sense. Looks like ratings. Here they're about 7. Here's a bad episode. But it looks like in general, they're not bigger than 10. They're not, 3.4 is the smallest one we saw, so probably not less than 0, right? Actually, it's quite a small data set, so we can look through it pretty quickly and determine what's going on. Okay, very good. So the next thing that we'll do is our usual, right? We want to filter the raw data set. Make sure that if there's any missing data, we delete observations with those missing data points. Otherwise, it'll contaminate our estimation. All right, so we'll do our filtering. And from the upper right, we can see that, yeah, it's still 176 observations, so we didn't drop any. So the data is complete. Okay, so every single episode in this TV show has kind of all the season, episode, name, year information, plus it has all the information on how many people rated that episode and how many, or what was the average rating that people gave. Okay. Very cool. So one thing that we might want to do, when we look at this TV show, we're like, okay, is it getting better or worse over time? And we saw in the lecture today or this week that this show seems to be like getting a little bit better over time. So how do we replicate that graph of showing just episode by episode, like what's the rating that people have supplied? So one thing you'll notice is that we do have episode number, but then it resets at the end of every season. Why is that important? Because one thing you might be tempted to do is to just run a ggplot and then points where we're like, okay, we'll have X be equal to episode and then Y be equal to that rating variable. But if we do that, we get this, which is not what we had in lecture, right? What we see here is because each episode number appears in multiple seasons, right? Like season 1 has an episode 1, but season 2 also has an episode 1. We're going to see, for each, here's episode 1, we're going to see 1, 2, 3, 4, 5, 6, 7, right? 7 episode 1s from each season. So what we need, is not that. What we need is a new variable that counts kind of the absolute episode number, right? Like relative to the very beginning of the show starting, kind of just counting sequentially upwards. So we know how to make a new random variable. It's the mutate command. So with our original data set, let's add another variable called epnum. Okay, and what we want epnum value to be is just whatever observation number it is in the data set. Okay, so we would like the first row to have a number of 1, second row 2, 26th row 26, 43rd row should be episode number 43. So what we'll do is, here's a new bit of code. You put 1 colon number of rows of DAT. Okay, so I'm not going to run this code. I'm going to go to the console and show you what these things do. So n row, that just gives us the number of rows in our data set. We can see 176. That's what we see in the upper right as well. 1 colon n row just creates a vector that counts up from 1 to 176. 1 colon something will just give you a count from 1, 2, 3, 4, 5. Okay. Cool. So we'll create this new variable, epnum. And now we can do our plot. Where X is epnum and Y is rating. All right, and that looks more like what we had in class, right? Perfect. Okay, cool. So yeah, what do we want to do with this data set? Here, this is kind of just like a demo data set to show you a few new techniques, running the regression and doing testing with robust standard errors, and then also doing a ggplot with kind of lines that are fitted to subsets of the data, which you're going to need for this week's homework. All right, so let's start off by asking the question, do later episodes of this show have statistically significantly higher quality? Right. So do later episodes of the show have higher quality, and is that relationship statistically significant? Well, how do we answer that? We can specify a linear model that regresses the rating on the episode number, right? As I increase the episode number, right, further and further along in the series, does the rating tend to be higher or does it tend to be lower? We can run this. And then we have reg 1 in our global environment up here. Now, before I show you summary is a way to kind of look at the regression output. Okay, and that's still true. So what we can see here is that epnum, it has a positive coefficient. What does that mean? It means that as you increase this x variable, the y variable on average tends to go up. So there is a positive association between the episode number and the reported quality of the series. Okay, let's look at the magnitude. It's 0.0044. So every next episode, so going from episode 2 to 3, leads to an increase in average quality of about 0.0044, right? And what are our quality numbers? They go from 0 to 10, right? So this is a fairly small improvement in quality, but we can see based on our p-value, it's significant at a less than 1% level, right? This number is less than 0.01, which means that, you know, we would fail to reject, or we would reject the null that this coefficient is equal to 0 with kind of less than 1%, at a less than 1% level. In other words, if it was really true that there was no relationship, that epnum had a 0 effect on average rating, so if that was really true, then the chance of drawing a sample such that we would see an estimate this positive is less than 1%. Actually, it's 0.156%, right? So if the null was actually true, then this would be a very, very, very unlikely sample to have drawn to see this big an estimate. So we conclude that the null is probably not true, right? Perfect. So this regression used regular standard errors, what in the lecture we called homoscedastic standard errors, where homoscedastic, remember, means that the sort of variance of the error around the regression line is roughly constant. For different values of x, the spread of the points around the regression line stays kind of roughly the same. So we can take a look. Let's add to our ggplot. We can add a straight line and just do a visual inspection to see, does it look like the spread of the points around the straight line is fairly constant? It's not totally clear. It looks like, you know, early on, maybe the spread is tighter, right? Like that the errors are sort of more tightly clustered around the line. And then by the end, the spread is maybe a little bit larger. The errors are sort of more spread, or the points, the y values are kind of more spread away from the line, right? So this suggests that, okay, yeah, maybe the error here is heteroskedastic. And for higher values of episode, you know, the error term kind of pushes the y further above the line or further below the line compared to earlier episodes. Okay, so how do we so what we're interested in doing is a t-test, but under the assumption that errors are actually heteroskedastic. Now, when we do summary and we see the p-value and the t-value reported here, that's actually homoscedastic errors. That's what's implemented by default in R. But we want heteroskedastic errors, okay? So let's use a new command called coeftest. And what we want is to test all of the coefficients on this regression that we've just run. And then we will add in this extra bit of code where the HC stands for heteroskedasticity consistent. So we want to test our coefficients using standard errors that are kind of accommodating the fact that the spread of u in y equals beta 0 plus beta 1x plus u, that spread of u is kind of larger for different values of x. Okay. And this is all we need to do. So we run this. Output looks very similar to the output from summary. We can see here that actually the standard error has, or the p-value has gone down a little bit, right? Oh, I'm sorry, it's gone up a little bit. That's what we expect, right? So with heteroskedastic error correction, when we do our tests, the p-value will almost always go up, which means that it becomes harder to reject the null, right? When the p-value is kind of getting bigger and bigger, we would fail to reject the null more often, right? Because as the p-value gets large, it's like, oh, the chance of seeing that coefficient, if the null is true, is actually quite high. So as we go to heteroskedastic errors, typically the p-value goes up, right? So maybe if we were significant at 1% before, we're no longer significant at 1%. Maybe now we're only significant at 5%, right? This is the sense in which heteroskedastic errors are more sort of robust, right? With the weaker assumptions, with allowing the spread of the errors to change, it kind of makes it harder for us to say anything about the relationship, but we want that, right? We don't want people to criticize our model and say, hey, but like, is this a real correlation you found? I know it says it's significant, but maybe you're making really strong assumptions. Heteroskedastic error is a weak assumption. It's saying, listen, like the spread of the error can be whatever. We don't need it to be the same all around the line. It can be whatever. And we still find significance, right? So that's what it means that it's a weaker assumption, but it leads us to have kind of a stronger conclusion, right? We're less susceptible to critiques from people who are, trying to figure out if what we have is real or not, in terms of, is our coefficient really actually significant? Okay. And notice if we don't specify this little bit with the vcov HC, we have 0.01565, which is exactly the same p-value as we got with just summary, right? So summary implements the homoscedastic errors. CoF test will replicate those homoscedastic errors if you don't feed it this additional parameter, which is the heteroskedasticity consistent standard error. Okay, so to answer this question, do later episodes have statistically significantly higher quality? The answer is yes. It's a small positive coefficient, and it's significant even once we account for heteroskedastic standard errors. Okay, and that's kind of it for testing this week. So, we can interpret the coefficient, we can test it. The tests that we have here are always relative to a null hypothesis that the coefficient is equal to 0. That's always the baseline. There are other ways to test where you can specify a different null, but I'm not going to do that right now because it's not something that you need. If you're interested, you can talk about it in office hours. The last thing we want to do is make this graph a little nicer looking and also see, okay, we have like an overall trend of positive as we kind of move, increasing episode numbers, we'll have a higher average rating, but within each season, does that tend to be true, right? We might be interested in that, okay? So one thing we can do is visualize that, and we'll create a visualization much like the one we have in the lecture slides. So we want to add individual trend lines by season, okay? So one thing that we need to do when we look at the data, season is a number, okay? So season is a number, which is fine. But just like when we did our bar plots of the like kind of average of Y by like say male, female, or college, no college, season is kind of like more descriptive. So like season 1, 2, 3, 4, 5, 6, 7, we would like those to be coded as kind of like factors. And what is a factor? A factor is like male, female. It's like, it's not necessarily that it's like a numeric value where like going from one to the next is always kind of like the same increment and meaningful. Going from one to the next is really just moving from one category to another category. Okay, so I'm going to create a new random variable, which is going to be called, let's say, just season fac. And we'll use this command as.factor to just convert the old season. And I'll show you what this does for us when we're doing the plotting. So let's create that new variable. And now let's start plotting. So we'll use DAT. We want our G on points still. Okay. And now what we want to do to replicate the graph we saw in lecture is we want different colors for different seasons, first of all. So we want to specify two new parameters in this aesthetic. Oh, so this should be AES. In this little aesthetics function. We've already done this a little bit before. We used fill on the bar plots to give different colors to different bars. So here we're using color, and then we're using something called group. So group is kind of something in the background. It doesn't create any visual difference, but it's like, hey, like each kind of group of episodes for each season, we're going to end up treating those as kind of like a different little cluster of points. Color is just what it sounds like. We're going to give different seasons a different color. All right, so let's plot this. So here's what we have. We have different colors for different seasons, right? Red, kind of this brownish color, green, and so on. Okay. Now, I told you, I would tell you what would happen, like why do we do season fac instead of season, right? When we look at our data set, oh, that's the old one. Doesn't update. Oh yeah, no, sorry, this is the raw data. So yeah, season fac, it looks just like season, except that we use this kind of as.factor command on it. What if we get rid of, what if we just say, well, let's just look at the original variable. What's wrong with season? On that. Okay. So this is kind of fine too, but what you'll notice on the right, the color is different. And on the right, the legend looks slightly different. What R is doing is it's treating each observation, each value of season as part of like a continuous scale, right? So it's like, oh, 1 is kind of the lowest, 7's the highest. So I'm going to put them all from sort of darkest blue to lightest blue, right? So R doesn't really care here that these are all just integer numbers. It's like, yeah, anything, it's just a scale of numbers, right? Versus when we did this kind of factor transformation, it's like, oh, each is a different category, right? So you're each going to get kind of like a very distinct color. They're not all on the same scale. Each one is distinct. All right, perfect. So that's one thing. Now we have different colors. And what do we want next? We want a different fitted trend line for each season. We'll still use epnum. Y is still our rating. But now we want to have group as season fac and color also as our season factor. So what we've done here is instead of just saying, okay, we have the X and the Y and that's it, like fit a line through it, we're saying, well, we have the X and the Y, but we want R to create a different line for each group, for each season. And that's what we see here, right? So now it's fit a tiny little linear regression for each cluster of points, okay? And we can see that although the overall trends over time of this show is to improve, we can see that that's not always the case within a season, right? So it looks like season 1, things were on the upswing, but then season 2 was quite poor, or poorer and poorer. Probably this line is driven a lot by this point down here, this outlier, which is by far the worst episode, apparently, of the entire series. But then in season 3, it seems to be kind of on the upswing. Then we have down a bit, up a bit, up a bit, and flat in the final season. So if we do still want to add an overall trend line, we can still do that. We'll just use exactly the same command as before without specifying the group or the color. Right, so that's our that blue thing is our kind of classic. One thing is, if you don't like the color that R has assigned to something, so if it's just like a single object, like this line, if you put a color outside this aesthetic list, then it's like, okay, R is saying like, just make everything to do with this object will be black, right? So that's now a black line. Okay, and last time, remember, we also had this this alpha parameter, or that was kind of like the transparency. If we want to take focus away from just individual points, outside the aesthetics, we can say, okay, every point you plot, I want it to have an alpha of 0.2. So I want it to be pretty transparent. Okay, now our points have become quite transparent, right? And the focus is really on the trend lines. As usual, change the theme and the axis labels. The Y label is pretty informative already, right? And so this is looking pretty good. Okay, perfect. So yeah, you'll need this functionality, drawing different trend lines for different groups of points within the data set for this week's homework. Okay, good. So that's it. I'm not going to get into the issues we discussed in class with respect to this data set. Remember, we were talking about sample selection. We were like, is the show actually getting better? Or is it just that fewer and fewer people are rating it, and the only ones left rating it actually really enjoy it? So I'm not going to get into that. We kind of talked enough about that in class. Here, this is just kind of a demo of heteroskedasticity, how you implement it, how you interpret the output, and then how do you plot multiple trend lines on a single plot for different subgroups of points. Okay, perfect. So that's it for this week. I'll see you guys in class during office hours in the tutorial. Take care.